Hi students, our study today about complex number. This is the third chapter. We're going to take it. A complex number is a number written of the form z equal a plus ib. A is called the real part, b is called the imaginary part, and I is equal root minus 1. It's called complex because we all know in the real number we cannot have square root of negative number. We have created a new set called complex where square root of negative number exists. So if b equal to 0 here, you're going to have z equal to a, so the number will be real. So that's why always r is a subset of the complex number. Why? The only case where r will be subset of a complex number is when b is equal to 0. For example, x squared equal minus 6, it was impossible in r, but it exists in complex number. So we know that x equal plus or minus radical minus 6. It can be split as radical minus 1 times radical 6. And since we are talking here in complex number, radical minus 1 is I, so we write it as plus or minus I radical 6. Similarly, x squared equal minus 16 impossible in R but exists in C. So x will be plus or minus radical minus 1 into radical 16. So radical minus 1 is I, so plus or minus 4 in C. X equal radical minus 3, since we are in complex number, so we say this can be written as I radical 3. Radical minus 8, it will be 2I radical 2. For example, if I give you a complex number z equals 7 minus radical minus 6, I write it as 7 minus I radical 6. So here the real part is 7 and imaginary part is minus radical 6. Similarly, here you have 2 minus radical minus 1 into radical 25, so 2 minus 5i. So real of z is 2 and imaginary of z is minus 5. So a complex number is always a number written of the form z equal a plus ib, where I is equal root minus 1. I is I, you all know radical minus 1. I square is minus 1. So I square is minus 1 because if you square, you get rid of the square root minus 1. I cube is I square times I, so minus 1 times I is minus I. I power 4, it means I square times I square, so minus 1 times minus 1 and 1. And if you continue, it will keep repeating. So that's why if you want to find I power 29, what do? You divide the 29 by 4. So it's 7. What is the remainder? Remainder 1, it's like I power 1, which is I. I18, you divide 18 by 4. You have remainder 2, so it's I square, which is minus 1. I43, remainder, if you divide by 4, it will be 3. So I cube is minus I. I20, remainder 0, so I power 0. I20, if you divide by 20 by 4, no remainder, so it will be I power 0, which is 1. So here it's 1. Sorry for this mistake. Here you can simplify it, 2I11, so it's 2I power 3 if you divide by 4. I16, so it's I power 0, so minus 7 I0, which is minus 7. 42 remainder is 2. 83 remainder is a 3. I square, you know, it's I square, which is minus 1. Minus 3i and minus 3i. I22, if you divide by 4, remainder 2. Now we have this one. 2i cube, it means minus 2i, because I cube is minus I. I power 0 is 1 minus 7. I square is always minus 1, so it will be minus 2. I cube is minus I times minus 3, it's plus 3i. Minus 2i square is minus 1, so plus 2. Minus 3i, minus 2. So now we add the real together. So what do we have as a real? Minus 7 minus 2 is minus 9. Minus 2i and plus 3i minus 3i, you have minus 9 minus 2i. Here, if you want to do this simplification, I square is minus 1, so it's a 3. I11 is I cube, which is minus I if you divide by 4, so it will be plus 2i. You square it, it's a plus b square, a square plus 2ab plus b square. So it's 9 plus 12i, and 2i squared is minus 4i squared, which is minus 4. So 9 minus 4 is 5 plus 12i. A complex number z equal a plus ib, and another complex number z prime equal a prime plus ib prime. If you want to add z to z prime, you add real to real, so it's a plus I prime, and you add imaginary to imaginary, so I into b plus b prime. If you want to do subtraction, so it will be a minus a prime, the real part, and b minus b prime, the imaginary part. If you want to multiply, you're going to get a prime plus I a b prime plus I b a prime. So I, the imaginary part, it's I, so I factor of b a prime, you can see it here, and plus a b prime. And the real part, it is a prime, you have ib times ib prime, so I square bb prime, but I square is minus 1, so minus bb prime. Example, if you want to add these two, you add real to real, so 3 plus 2i. If you want to subtract, 2 minus 1 is 1, minus 3i minus 5i minus 8i. If you want to multiply, it's 2 plus 10i minus 3i plus minus 15i squared. But minus 15i squared is plus 15, so you're going to get this answer. However, you can use directly in complex number the calculator. It doesn't matter. You can get the answer directly. Conjugate of a complex number. If z equal a plus ib, its conjugate denoted by z bar, it's equal a minus bi. You don't change a, the real part will keep the same, but you change the imaginary part. Bi will be minus bi. Why we need this? We need this because this is very important when you multiply z by z bar. Why? You know that a minus b into a plus b is a square minus b square. So if you want to multiply a plus ib into a minus ib, you're going to get a square minus I2 b2. But I square is minus 1, so you're going to get a square plus b square. So always a complex number times its conjugate, it's always equal real square plus imaginary square. So here this is not a complex number, this is ordinary 1, 4 minus x squared. Here you have z times z bar, this is z, this is its conjugate. So z times z bar here directly, it's the real part, which is a square 4, plus always plus 3 square, which is 9. Because it is a square minus b square, so 4 minus 9 I square minus 9 I square is plus 9, so it's equal to 13. Here the same story, it's x square plus 49. When you want to divide a complex number by itself, I know you can use the calculator directly and you get this answer, so no need for to do it. But however, we need to solve these problems because sometimes, most of the time, we have parameters. So that's why if you have 2 minus 3i over 1 plus 5i, and I want to write, you have a complex over complex, and I want to write it in a complex number where I know the real part and I know the imaginary part. So what do? I multiply by the conjugate of 1 plus 5i, which is 1 minus 5i, up and down. So here you're going to get 2 minus 10i minus 3i plus 15i squared, which is minus 15, as you can see here. A plus ib into a minus ib is 1 plus 25. So you're going to get 2 minus 15 minus 13 over 26 minus half, and minus 13i over 26 is minus half I. So we had a complex over complex. Now we're going to get a complex where real part is minus half and imaginary part is minus half. Now, the point M is called the image of a complex number z equal a plus ib, and the complex number z equal a plus ib is called the affix of point M. We write it as m of z or m of affix z or zm. And if you write it as m of z or z of m, it's the same. We say m of affix z or z of affix m. Why we're going to write it like this? Because a complex number can be written, if you have, for example, 2 plus 3i, here you can take it as a point m of z or z of m, whose components, for example, 2 and 3. So you have the x, y axis. The x axis will be the real axis, okay, the real one, and the y axis will be the imaginary, so I. So here you have 2 and 3. So this will be z. And if you take z bar of this number, which is equal to minus 3i, it will be symmetric with respect to the y-axis. Why? Because you're going to have the same x. For example, sorry, here it's symmetric with respect to the x-axis, not the y-axis. You have the same x but different y. So always z and z bar are symmetric with respect to the x-axis. And the modulo is always radical a square plus b square. Why? Because if you have this complex number, for example, and if you want to find the modulo is the distance, always the absolute value from the origin. So if you do this rectangle here this is 3, this is 2, so it will be radical a square plus b square. So always the modulo of a complex number is equal radical a square plus b square. So here if you have this example, so the modulo will be radical 4 plus radical 9, which is radical 13. So a complex number is written of the form Zm, and we say Z of affix m, and where you have ordered pairs, A will be the real part, B the imaginary part, and if you want to find root of Zm, this is nothing else than root a square plus b square. Now properties of the modulo. Z and norm of ZA times norm of ZB, you can split it, norm of ZA times norm of ZB. ZA over ZB norm, you can do each one alone, and if you have the power, you can put it outside. Example, if you want to find the norm of that one, no need to do the multiplication, then times conjugate, get the number, and then do the norm. So directly you do norm of 2 minus 3i over norm of 1 minus i into norm of 2i. This is of the form radical a square plus b square, so it's 4 plus 9. Here it is radical a square plus b square. A is 1 and b is minus 1. If you square a, it will be radical 1 plus radical 1, which is radical 2. And here it will be radical 4 because I don't have a. Radical 4 is 2. Here you have 3 minus I power 10. So we take the 10 outside. We do the norm here. It will be radical 9 plus 1. This is wrong. Radical 9 plus 1 here. It will be radical 10. And you have it power 10. So it will be 10 power 5. Okay? Plus IB, Z bar equal A minus IB, symmetric with respect to the x-axis. Example, Z equal 2 minus 3i, Z bar equal 2 plus 3i. Sometimes when you want to show that Z and Z bar in the problems are, if you want to show that Z is real, we need to show that Z equals Z bar. Why? Because Z equal A plus IB. If A plus IB was equal A minus IB, so impossible for these two to be equal, and here you have plus IB and minus IB. If they are equal, it means I don't have imaginary part. So that's why when Z equals Z bar, if you prove that Z equals Z bar, we are showing that Z is real. And if you prove that Z equal minus Z bar, we are proving that Z is imaginary. Why? Because you're going to get A plus IB, and if you put minus here outside, you're going to get minus A plus IB. So if these two are equal, it means impossible here to have A and minus A to be equal. So you're going to have IB equal IB. So if you show that Z equal minus Z bar in some problems, you are showing that Z is imaginary. In imaginary, we don't have, it's of the form IB. Properties. Z times Z bar is x plus iy into x minus iy, which is equal x square plus y square. But we know norm of Z is radical x square plus y square. But x square plus I square is Z bar, so it's square root of Z bar. So if you square both sides, so norm of z square, don't forget, is equal z bar. So norm of z square equal z bar. Conjugate of za times zb, you can split each conjugate alone. If you have a conjugate for the whole one, za over zb, you can do conjugate of za over conjugate of zb. If you have a plus, you can split. If you have minus also, you can split. Always for multiplication, division, sum, you can split the conjugate. Here in this example, if you have you want to find the modulo here, this is a repetition. This is radical 4 plus 9. Here it will be 25 plus 1. Here it will be a square plus b square 1 plus 16 times 3, which is 7. Here you do up alone, down alone. So it will be 1, and norm of I is 1 because b is 1. Radical of 1 square is 1. Here you can split each one alone. It will be 4 plus 9. Radical 13 into radical 2. And here you can do the 2 plus I alone, which is radical 5. Radical 5 power 5. Okay.